Hello, welcome to this video presentation. I would like to give you a brief overview of the results we have on simple topological drawings of k-planar graphs. How close a graph is to being a planar graph can be quantified in multiple methods. One of the methods is counting the maximum crossings per edge. It's also called as the local crossing number. In other words, if a drawing has at most k edges per edge, then the corresponding graph is called a k-planar graph. We could consider the case of k4 or a complete graph on 4 vertices, which is a planar graph. Another example is k5, which has a drawing where each edge is crossed at most once, hence a k5 is one planar graph. However, when you look at K7, it has a drawing where each edge has at most 2 crossings, and K7 is a 2-planar graph. We could also consider the crossing number as a quantity. We count the total number of crossings in a graph, which is called as the crossing number. Let's look at an example. In this subgraph, we could read out the top edge into this blue edge in order to decrease the total crossings in the graph. We could further decrease the number of crossings by rerouting other edges in this graph. When we talk about drawings, we could also add restrictions to how multiple edges interact with each other. Simple topological drawings are drawings where any two edges have at most one point in common. Two edges are not allowed to cross each other more than once, and adjacent edges cannot cross each other. In other words, two edges can cross at most once, and adjacent edges are not allowed to cross. The simple local crossing number is defined as the maximum crossings per edge in a simple drawing. Now, a natural question to ask is how the local crossing number is related to the simple crossing number. Intuitively, we can observe that if you decrease the total crossings in a graph, we would end up with a simple drawing. However, when you try to decrease the maximum number of crossings per edge, does it also give us a simple drawing? Turns out, not always. For k-planar graphs where k is 1, 2 or 3, it has been proved that minimizing total crossings also minimizes the maximum crossings per edge. However, the same is not true for 4-planar graphs. In other words, we have examples of 4-planar graphs where the 4-planarity is lost if we add the restriction of simple drawings. So now we know that 4-planar graphs cannot always be drawn as 4-plane simple drawings. So can they be drawn as 3290 plane simple topological drawing? Yes. But what about some other smaller number? Once we answer this question for 4-planar graphs, we would also want to ask this question for general k-planar graphs. So the question is, does there always exist a function f such that every k-planar graph has an f of k plane simple drawing? In this paper, we answered this question in the affirmative and showed that the simple local crossing number of a graph is bounded by a function of the local crossing number. Let's look at how we do this. Two edges cannot cross each other more than once, and adjacent edges cannot cross each other. So when two edges cross each other more than once, we call the substructure a lens. And the subparts of these edges which are involved in the lens are called as arcs. To get rid of at least one of these crossings, what we try to do is reroute one of the edges such that we get rid of at least one crossing. What makes sense to do is reroute the edge with a higher number of crossings towards the edge with the lower number of crossings. So in both these cases, we end up with something like this. However, there's a small problem associated with this. Assume we had these green edges in this graph. What happened after rerouting is that the green edges along with the rerouted edges formed new lens, and the number of crossings on the green edges increased. Using this basic approach, we were finding it hard to count the number of crossings. So we needed something more, some additional parameter which would help us analyze the situation. So we went ahead with something called the planarization approach. So let's take this example of a four-plane drawing of a four-planar graph. We obtain a network of this graph by adding nodes at each crossing of the graph, of the drawing. So the new nodes along with the original nodes of the graph form something called the network. A property of this network is that any edge has a combinatorial length of at most k plus 1. Let's look at how we reroute lens in this approach. So we always use the network as a base for rerouting the lens to get rid of crossings. So this is a lens formed by edges which cross more than once. So we look at the length of the arcs. The top arc has a length of 2 and the bottom arc has a length of 3. So we reroute the bottom arc towards the top arc because we always try to decrease the length of the arcs whenever possible. Let's look at this length which is formed by these two adjacent edges which cross each other. When we consider the length of these arcs, the length remains the same for both of them. Hence, we count the number of crossings of the arcs. The bottom arc now has 0 crossings, but the top arc has 2 crossings. So we reroute the top arc towards the bottom arc. What we also try to do through this process is to ensure that any new crossings that are introduced are always in a small neighborhood of a node of n. Let's look at one node of the network. An edge passing through this network V could potentially cross every other edge passing through the same node V. It turns out we can bound the number of edges passing through any node of the network. We also know that any edge has at most k number of nodes. Both of these bounds put together shows that the maximum crossings per edge is indeed bounded. This answers the question posed by Schaefer. Let us look at this in more detail. So we see this node V, and we want to bound the number of edges passing through this node V. We look at all the edges passing through this node V and take the subgraph induced by these edges. And we would like to count the number of vertices incident to these edges. The thing to note is that any edge passing through this node V has 4 directions to go to. Suppose the edge goes towards the bottom. Then it has 3 directions to go to, and any edge has a combinatorial length of at most k plus 1. So the number of edges which are incident can be bounded using this number. Now, since the number of edges passing through this node is bounded, and we also know that the number of nodes on an edge is bounded, we can bound the total number of crossings. To conclude, the simple local crossing number can be bounded by a function of the local crossing number. More specifically, this is the function we obtained. As you can observe, this function is exponential in k. So can the bounds be further improved? Another natural question to ask is to find lower bounds. We know that four-planar graphs cannot be drawn as four-plane simple drawings. But is there some other lower bound that we can achieve? These are some directions in which this work can be continued. Thank you.